All right, welcome to this lecture in your course on mechanical operations. In the last few lectures, we have dealt with a few mechanical operations. We looked at various methods of mechanical separations, including screening, sieving, sedimentation, filtration. And then we looked at the process of size reduction or comminution and various methods for doing the size reduction and the energetics involved in the process. So, today in the next couple of lectures, we are going to look at another important mechanical operation involving particulate materials, which is storage and transport. In any factory, the raw materials that are to be used in the process have to be stored in fairly large quantities. And then as and when you need them, they have to be taken out of storage and used. So, the storage of solids is an important consideration for process engineers. So, what is the difficulty in solids compared to storing liquids? If you look at a typical container that contains a liquid versus one that contains solids of various shapes and sizes and so on, there are some similarities and some dissimilarities. The similarities between a liquid and a particulate mass, and here we are talking about dry storage. This is not particles in suspension, but particles that are stored in dry condition like powders, grains and so on. The liquid will obviously exert a pressure on the walls and the bottom of the container that it's stored in, and so will particles. So, they are both capable of exerting pressure on the sides of the container that they are stored in. And if you provide an opening, the liquid will flow through, and similarly here if you provide an opening, the solids will discharge as well. So, in those respects they behave very analogous. So, what are the differences? The most important difference is that in a liquid, when you apply a pressure to it, the molecules kind of adjust to each other, they slide over each other, and so which is represented as viscosity, but it enables the liquid which is under pressure to flow fairly smoothly, and we are talking about basically Newtonian liquids, for example water. In fact, in many aspects the behavior of particulate masses is very similar to a non-Newtonian liquid or what is known as a viscoplastic liquid. But in general, in our experience, if you apply pressure to a liquid, it will flow because the molecules are able to slide over each other. But in a particulate mass, if you apply pressure, the particles are not going to be able to as easily slide over each other. In fact, they will tend to interlock. As soon as you apply a certain pressure, the solids, if anything, will start resisting any flow or any motion. So, that is the first characteristic that is different about a particulate mass. And in fact, up to a certain pressure or force, this particulate mass will resist any kind of distortion. It will just stay intact. As you keep increasing the pressure, once you go to a high enough force applied on this particle mass, failure will occur, and then the particle mass will start flowing or it will start breaking apart, so to speak. So, it is a very highly nonlinear behavior. There is actually a threshold force above which failure occurs, and then the particles can start sliding over each other and movement can begin. But then what happens is, as the particles layers slide over each other, there is a very high coefficient of friction, and this friction is again reflected in the requirement of higher energy to get the same flow throughput as you can get with a liquid. And so, in many ways a particulate mass behaves in a way that is very different from a Newtonian liquid. What this again translates to is, in a liquid, if you apply a certain pressure, the pressure will be transmitted fairly equally in all directions. In a particulate mass, the pressure, the applied pressure and the transmitted pressure can be very, very different. In fact, the pressure that is transmitted into the particulate mass is typically lower than the applied pressure, and in fact in a direction that is perpendicular to the applied force or applied pressure, the pressure transmitted is a minimum. Okay, so that is one difference based on pressure distribution. The second is shear stress effect. So, what happens if you take a liquid that is stored and apply a shear to it? Basically, the entire fluid will start moving as per the shear force that is applied. In the case of a particulate mass, when you apply a shear stress at one point, it takes time and work to transmit this shear through the entire particulate matter. And here again, up to a certain shear stress, the entire mass will behave as a whole. It is only beyond a certain shearing stress that you will start to see again layer wise demarcation of flow behavior. So, in terms of shear stress also, there is a certain threshold value above which a particulate mass will start behaving like a liquid that's stored in the container. The third difference is in terms of density distribution. In the case of a liquid, obviously density will depend on pressure and temperature, and if you take individual particles, again the density is set by the structure of the particle and the temperature and pressure and so on. But in the case of a particulate mass that is stored in a container, the critical density is not the density of the particle, but what is known as the bulk density. The local density at any point depends on how the particles are packed in that area. So, if you have loose packing, you have a low bulk density, and if you have tight packing, you have a high bulk density. So, the density in the case of a particulate mass is mostly a function of the interlocking behavior between the particles. The greater the interlocking, the greater the cohesion between the particles, essentially the more accommodating the particles are to each other, the greater the concentration of particles at any one point, the greater will be the bulk density. So, that is the other major difference. The fourth is cohesiveness. Particles can behave very differently if they have cohesive characteristics versus non-cohesive characteristics. This we have discussed earlier in the context of our discussion on cohesion, but a sticky particle mass, for example wet cement or suspension of nanoparticles or even nanoparticles that are stored in powder form, all exhibit high levels of stickiness or cohesiveness. So, their flow behavior and their storage behavior will be very different compared to something that is essentially a dry solid material that's stored. For example, again it could be rice granules, or it could be sand, or it could be ash particles, or it could be just grains of food grains, for example. They all tend to behave more like non-cohesive particulates, and so their characteristics will be very different. So, these are the important qualitative considerations to keep in mind when you talk about storage of particles versus storage of a liquid. And all of these have to be taken into account when you design a storage container, and you also design for charging and discharging of these containers. So, one of the key parameters here is this ratio of PL to PV, which is the pressure in a normal direction to pressure applied to applied pressure, and it is indicated by a symbol K prime. As I said, the pressure in a normal direction is at a minimum compared to the applied pressure. In fact, K prime is approximately equal to, for a cohesive solid. What do you think K prime will be for a cohesive material? Be very close to 0. In other words, there is no guarantee that any pressure that you apply is ever going to get transmitted in a normal direction. And for non-cohesive solids, it varies somewhere between 0.3 to 0.6 for non-cohesive. Now, this has important implications both for how particles are stored in a container and also how they flow into and out of a container, as we will see. So, what you really want to know is, for an applied pressure PV with a normal pressure of PL, what is the pressure distribution as a function of theta, which is an angle between normal and horizontal. So, in order to do that, you can model granular material in a container and look at the pressure distribution. And one way to do that is to take a right angled triangle. This is a right angle, and let us say that the base of this triangle you are applying the pressure PV, and that results in a normal pressure PL, which is normal to that, and you want to know what is P at any angle theta, right, because that will give you the pressure transmission characteristics for this particulate solid. So, how do you, so let us take a cross section, it is a right angled triangle of length, let us say that this length is some dl, that is the hypotenuse. So, this length will be dl sin theta and this length will be dl cos theta, and let us say that the breadth is b. So, b times dl gives you the area. Now, at any theta, or PV and PL, is this an equilibrium? If you look at this picture, can this be the equilibrium stress distribution for this triangular element, or what is missing?
Gravity.
No, I don't. This, we are just looking at the pressure stresses inside the thing. Shear stress, because the shear is going to be balancing the pressure. Shear is absent in the direction of the applied shear, applied pressure. Shear is also absent in the normal direction, but at all other angles there is a shear stress that is counteracting the stress that is due to the applied pressure. So, that has to be taken into account also. So, we can do the force balance in the direction normal direction and the horizontal direction, and when you do that you will come up with P times B dl equals PL times B dl times sin squared theta plus PV times B dl times cos squared theta. Now, cancelling out the B dl's, P is equal to PL times, because you can write sin squared theta as 1 minus cos squared theta plus PV times cos squared theta, or this is equal to PV minus PL times cos square theta plus PL. Again, PV is the pressure, applied pressure, and PL is the pressure in a direction normal to it. And similarly, if you do the force balance in a direction that is parallel, tau will come out as PV minus PL times cos theta times sin theta. So, these are the expressions of P and tau as a function of any general theta. So, what does this imply? So, let us take the case where theta equals 0. So, cos theta equals 1, P will be equal to PV and tau will be equal to 0. And when theta equals 90, P will be equal to PL and tau will be equal to 0. And in fact, if you calculate various values of P and tau as a function of theta and then you plot them, what you will come up with is a figure that is basically a circle. So, if you plot P on the x axis and tau on the y axis, and let us say that this corresponds to tau equals 0, let us say this corresponds to P equals PL and this corresponds to P equals PV. So, tau equals 0 when P equals PL and tau equals 0 when P equals PV, and actually if you then calculate the values, basically what you come up with is a circle that represents the relationship between P and tau. This is called the Mohr stress circle. So, the way this works is, if you take any angle alpha from the center, then tan of alpha will give you tau over P. And by the way, the radius of this of course is radius equals P, sorry, this should be P, yeah, so it should be PV minus PL by 2, and the distance from the origin to the center is PV plus PL by 2. Okay. So, when is the shear stress likely to be a maximum? When you draw a tangent to this curve, this angle that the tangent that the line that's tangent subtends is called alpha m, and the value of alpha m, by the way, this alpha m is called the angle of internal friction, and alpha m is such that sine of alpha m from this triangle is going to be equal to PV minus PL over 2 divided by PV plus PL over 2, or sine alpha m equals PV minus PL over PV plus PL, right. Or in terms of, if you remember, we had defined K prime as PL over PV. So, you can write sine alpha m as 1 minus K prime over 1 plus K prime, or you can write K prime as 1 minus sine alpha m over 1 plus sine alpha m. So, which is equal to PL over PV. So, that is an important relationship in itself. If you know the so called angle of internal friction, you can calculate how the normal pressure varies for a given applied pressure. So, K prime, as we said before, varies for a non-cohesive suspension from about 0.3 to 0.6. So, this alpha m actually would vary as somewhere between 15 to 30 degrees for a non-cohesive particulate mass. So, if you look at this, the clearly tau has its maximum value when it is at that value of alpha m, and the circle itself is known as the Mohr rupture envelope. This kind of a behavior can be observed when you have a particulate solid that is non-cohesive and also fairly homogeneous in nature. If you have a cohesive solid, then the tangents here do not necessarily go through the origin. So, they are likely to intersect the vertical axis either above or below the 0 point. So, a cohesive homogeneous solid will have a very different behavior from a non-cohesive homogeneous solid, and also a homogeneous solid itself will have a very different behavior from a heterogeneous solid. Now, in terms of storage of solid particulates, what do we mean by homogeneous and heterogeneous? It has primarily to do with the density distribution. As I mentioned earlier, the local density can be very, very different depending on the local packing condition, so to speak. And by homogeneous, we mean that the density distribution is very uniform. When you talk about, when you get into fluid mechanics, there is a lot of discussion about compressible and incompressible flow, and one of the definitions of incompressible flow is that the density of flow must be non-varying along the streamline of flow. So, that is another principle that particulate masses violate, in the sense that, let us say that you open your silo and the particles start flowing down. So, the streamline is essentially a vertical downflow, but the density can vary quite significantly along this direction of flow, which violates the principle of incompressible flow. So, many of the theories that you may have already read or you will be reading about fluid mechanics rely upon incompressible flow characteristics, and that is another major difference between particulate mass storage and flow compared to liquid storage and flow. So, another parameter that is of interest in storage is what is known as the angle of repose. By the way, if you take tan of this alpha m parameter, that gives you the coefficient of internal friction. When you store solids in a container, they don't stack themselves in a very uniform fashion. There is always an angle of storage, and it typically would look like it makes an angle both with the vertical walls as well as with a horizontal surface. If you see how grains settle onto the bottom of a container, or how they stack themselves against the walls of a container, there is always a small angle. They do not perfectly align themselves to the vertical wall or to the horizontal surface, and that is called the angle of repose. This angle of repose is theoretically equal to the alpha m value, but that only applies again for completely non-cohesive and fully homogeneous particulate masses. Almost in reality it never happens, and the reason for that is that when you look at how particles in a bulk behave versus particles near solid surfaces, the behavior is very different. For one thing, particles in the bulk have many more neighbor particles around them, whereas particles near the surfaces have only the surface on one side. So, the number of nearest particle neighbors is almost half for particles on the peripheries compared to particles in the bulk of the particulate material. And because of that, particles on the periphery, the ones that are in contact with the walls and the bottom of the container, tend to have much less sticky behavior, tend to behave more like a non-cohesive solid, and they tend to have what we call dry behavior. They do not behave as a wet slurry. And so, most of the time alpha r is smaller than alpha m, and it can be significantly smaller than alpha m, but its maximum value is the angle of internal friction or alpha m. The value of alpha r as well as the value of alpha m have a lot of implications for not only how particles are stored, but also how they flow, because this so called angle of repose and the angle of internal friction dictate two things. One is alpha m controls how, when you let us say that you open the bottom and you start discharging the solids, the behavior initially, I mean the way that material would discharge out of a bin, typically the material right in the middle will start discharging first, right. I mean if you have, I do not know if you have had any experience where you store things, open up and see how the material flows, but the initial flow of material will be the column of material that is right on top of the opening. Slowly it will take a kind of a funnel like form, it will slowly start expanding, and after a certain point the particles that are near the walls will start discharging, and the last piece of material to discharge will be the material that is already on the floor. It has to eventually migrate to where the opening is and start flowing out. So, that is the time sequence of how discharge happens, and if you look at what controls this behavior, the initial flow where the column starts to flow, as well as the conicular or funicular flow when it slowly starts to expand into a horizon, into a cone, are controlled by the value of alpha m. Whereas, once the flow has been set in motion and you start having participation from the material along the walls or at the bottom, then the angle of repose has a significant influence. Essentially the way you can look at this is, the higher the angle of repose, the more easy it is to dislodge the particles from the surfaces they are in contact with and have them start moving in along with the rest of the flow. Whereas, if they do have there is a significant angle of, or if the angle of repose is 0, then it essentially says all the material is well lined up and well adhered to the surfaces that they are in contact with. It is going to take more time, more force to start them in motion. So, for good flow, what you would like is a low angle of internal friction, which also results in a low coefficient of internal friction between the layers as they start to flow, which again means there will be less temperature rise, there will be less energy input to achieve the same amount of particulate flow and all that. And you also want an angle of repose that is fairly high. You want the particles layers near the walls and the container bottom to be ready to leave as soon as flow sets in. So, if you look at how this fits into the storage of solids, the general case that we have taken is one that is usually how solids are stored indoors. But if you look at how solids are stored, for example, if you go to a power plant, you will see large mounds of coal that are just stacked outdoor, right. Now, when do you want to stack materials outdoor? It is usually for insoluble material, because you should if suddenly there is rain, you do not want the whole thing to be washed away. And it is also material that can be easily transported to your process by using a shovel, scoop, crane that can just lift material from wherever it is sitting on the outside and taking it to where your process is. In the case of bad weather, usually there are big plastic sheets and tarpaulins that are used to cover these mounds. So, when you talk about storage of particles, we are not always talking about storing them under highly controlled conditions and then precisely controlling how they flow in and out of the container. Again, you should visit a power plant sometime if you want to know how solids are stored. There are trucks that come and just dump mounds of coal onto the floor, and then as and when the power plant needs coal, they just scoop some out and use them. But in general, the kind of processes that we are talking about have to do with storage in containers in indoor environments, and in those cases there are 3 types of containers that are used. They are called silos, bins and hoppers. The difference between them is a silo is typically a tall container of relatively small diameter. A bin is shorter and broader, wider. A hopper is something that is kind of like a bin but even smaller. So, a hopper is used for very temporary storage. It is typically used between stages in a process. So, if you have one process step and the next process step and you just need to store some materials for a certain period of time, use a hopper to do that and then take it out and use it in the next stage. So, the silos are typically made of concrete or they are made of some metal, and when you store in silos, typically the filling is done by kind of an elevator type of arrangement where there is some mechanism that lifts the material and always fills from the top, whereas the discharge is virtually always through chutes that are open at the bottom. So, the typical material flow is designed to be first in first out. The layer that is put in first thing into the container is also what discharges. Now, the way you do not want to use bins is where you store and then you take out also from the top. If you are charging and discharging are from the top, then you probably will be violating this principle of first in first out. So, an ideal process flow in this case is fill from the top and take out from the bottom. And as you do that, as I said, essentially you go through various stages of discharge. Initially this column discharges and then starts to expand to include all the material that is in the bin. One thing you have to watch for as you are doing this process is whether this type of flow is going through these stages. Sometimes what can happen is the central column will discharge, but if the connectivity to the rest of the material around it is poor, the discharge may stop at that point or it may become intermittent. So, one of the key things to look out for when you are discharging material from bulk storage is whether you are getting continuous flow. If you are seeing a pattern where you have high flow rates followed by low flow rates, then you know that the discharging process is not working as well as it should. One of the reasons for that is humidity. Even though the particles as packed may be dry, wetness or stickiness can develop over time, particularly places like Chennai where you have high temperature and humidity. Unless you have active humidity controls in your storage chamber, it is very likely that the humidity will be absorbed by the particles and they will start forming these liquid bridges and the solid bridges that we talked about earlier. Once that happens, then material that was originally non-cohesive to begin with can over time become cohesive in nature, and therefore its flow characteristics will start to change very rapidly. So, environmental controls are very important, and so typically what they will do is put a cap on top of the bin or silo, and this will be sealed, and so that you can control temperature and humidity inside this silo. The only time you open it is for the charging, and then you immediately close this again. In fact, what we will do in the next class, we will take a look at some bins and silos that are used in manufacturing industries. I have a couple of movies also of how sometimes these silos can fail. The worst thing that can happen is for a silo in which you are filling material to come crashing down, and that can happen if you are not careful about how you control its operation. And we will also take a look at how these caps are used on top of bins to control the local environment and make sure that the collapse does not happen. One of the reasons again for a bin to collapse is obviously it collapses when the pressure that is exerted on the sides becomes too high, and that can happen when the particles, instead of being free flowing and dry material, become slurries that have very high cohesion, and therefore any pressure that you apply to get them to discharge results in very high stress around the periphery of where the particles are being stored, and therefore cause a structural failure of the silo. So, we will take a look at some pictures and some couple of videos on how these storage structures can fail. And also the other thing we need to look at is, in a silo, how is pressure distributed as flow sets in? How is the outflow going to affect the distribution of pressure inside a silo, and how do we optimize that? So, these are some of the things that we will look at in the next couple of classes. Any questions? Okay, see you tomorrow.